Hey everyone, today we'll be talking about implicit differentiation. Let's get started. Imagine you're asked to find the derivative of a function that has both x and y. There's no way you can rearrange it to write it as y of f of x. What do you do then? Well, there's a method called implicit differentiation, which allows you to find the derivative of that function. For functions defined implicitly by a relation between an independent variable and dependent variable, in most cases x and y, you must use the method of implicit differentiation. This technique allows you to find the derivative of y with respect to x without having to rearrange or solve the equation for y, because in most cases it's time-consuming or impossible. We're given the equation 1 over x plus 1 over y equals 1. We're asked to find y prime using implicit differentiation in part A, and in part B, solve the equation explicitly for y, and then differentiate to get y prime in terms of x. Finally, in part C, we are asked to compare our two expressions to see if they're the same. In part A, we're asked to find y prime using implicit differentiation. So our method for this would be to first differentiate both sides of the equation with respect to x, which is our independent variable, and then solve the resulting equation for y prime, which is our unknown. So we'll start off by applying the d by dx operator to both sides. It's essential to start off by applying the d by dx operator on both sides of the equation. Since we are differentiating implicitly, we apply the d by dx operator to both sides of the equation. And recall, that just means what variable you are taking the derivative with respect to. So in this problem, we are taking the derivative with respect to x. Applying our rules of differentiation, we use that to differentiate each term. So here we apply the sum rule since f and g are differentiable functions. So now we have d by dx of 1 over x plus d by dx of 1 over y is equal to d by dx of a constant 1. Since the derivative of a constant is always equal to 0, on the right-hand side, when we have d by dx of 1, that is equal to 0. Next, we must treat y as a variable, but y is currently a function of x. So we must differentiate with respect to y, and then differentiate the dependent variable y with respect to x. Now they are the same variables. Rewriting 1 over x as x to the power of negative 1, we now have d by dx of x to the power of negative 1 plus d by dy of 1 over y times dy over dx, and that is equal to 0. So again, the derivative of a constant is 0, and we will be applying the power rule and chain rule. By applying the power rule, we get negative x to the power of negative 2 for the first term, plus negative y to the power of negative 2, multiplied by y prime. Now we are simplifying the expression to make rearranging and solving for y prime easier. So now we have negative 1 over x squared plus negative 1 over y squared multiplied by that y prime, and that is of course equal to 0. So now we are rearranging and solving for y prime by moving all y prime terms to one side, the left-hand side, and moving all other terms to the right-hand side. So now we have negative 1 over y squared multiplied by y prime is equal to 1 over x squared. We are now factoring out the y prime variable on the left-hand side and dividing both sides of the equation by the factor in front of that y prime. Dividing by the factor of negative 1 over y squared, we get y prime is equal to 1 over x squared divided by negative 1 over y squared. That is our y prime, but we can rewrite that and simplify it, getting y prime is equal to negative y squared over x squared. So our final answer in part A is y prime is equal to negative y squared over x squared. In part B, we will now solve the equation explicitly and then differentiate y prime in terms of x. So our method would be to first rearrange the equation solving for y, and then differentiate explicitly to get y prime in terms of x. Rearranging the equation to solve for y, we get y is equal to x over x minus 1. Since we are taking the derivative, we apply the d by dx operator to both sides. In order to continue differentiating explicitly, we must apply the quotient rule. Applying the quotient rule and then simplifying, we get dy over dx is equal to brackets x minus 1 subtract x divided by x minus 1 squared. Now simplifying our derivative expression, we get y prime is now equal to negative 1 over x minus 1 in brackets squared. So now our final answer for part B, by solving explicitly, we get y prime is equal to negative 1 over x minus 1 in brackets squared. In part C, we were asked to compare two expressions from part A and B and see if they are the same. However, we can't compare our expressions just yet because in part A, our y prime still has a y variable in it. So recall the equation for y which we solved for in part B. Substituting the equation for y into our y prime expression from part A, we get y prime is equal to negative in brackets x over x minus 1 squared over x squared. We can now simplify the y prime expression by doing keep, change, flip. So in the end, we get y prime is equal to negative 1 divided by, in brackets, x subtract 1 squared. So now we can compare our two expressions and conclude that yes, our y prime expressions are the same. Now for interest's sake, let's look at it geographically. So here graphed on Desmos is our y prime expression, y equation, and a vertical asymptote. Our domain of this function would be what? Well, our domain is when our function, which is our y prime expression, is equal to 0. So for our y prime expression, that would be our domain is x cannot equal 1. Solving for critical points, we see that x equals 1 is 1. However, recall that x equals 1 is not in our domain. Therefore, there are no critical points in this function. It is also concave down on negative infinity to 1 and concave up on 1 to infinity since f double prime is greater than 0. Thanks so much for listening and watching, and I hope you have a better understanding of implicit differentiation.